Okay, notes 14 is definition of an nth root. So we're going to talk about the definition of a square root, definition of an nth root, how to find roots of variable expressions. I'll talk a little bit about the Pythagorean theorem again, and then a little bit about radical functions. So we're finishing up rational functions. Now we're going to go into radical functions. And radical functions are functions that have a radical. So like a square root, a cube root, a fourth root, etc. Okay. So first, the definition of a square root. We say that b is a square root of a if the square root of b squared equals a. So this is more like the formal definition of what a square root is. Okay. We all know that the basic square roots, like the square root of 25 is 5, the square root of 64 is 8. This is just those square roots following this formal definition. Okay. So in the first couple examples, it says identify the square roots of the real numbers. So what that means is it wants us to take the square root, if we can, of each of these numbers. So the first one would be the square root of 25, which is 5. Okay. Then you do the square root of 49, 7. What about the square root of 0? 0. Can you take the square root of a negative number? No. So this would be no solution. So again, you guys are able to do that fairly quickly because you know that 25 is the same as 5 times 5. Okay, just like 49 is the same as 7 times 7, and 0 is the same as 0 times 0. So if we have those repeated values, that tells us it's a perfect square, and we're able to take the square root and get a whole number. Okay. So then it says more formal definitions of the square root. It says let a represent a positive real number, then the square root of a is the positive square root of a. All this means is if you take the square root of a positive number, you should get a positive number back. So square root of a positive number will give us a positive number. That's it. Okay. This is called a principal square root, which means when you think of square roots, you think of the principal square root. The most basic square roots that if you took that square root, you will get an answer. Okay. The other ones are called negative square roots, and they're called negative square roots because there's a minus sign in the front. Okay, so that's completely different than example D, because example D had our minus sign inside of the square root. Okay, so if it's outside, then it's a negative square root. And then, of course, the square root of 0 equals 0. Yes? The entire notes?
Not entire notes, this part. The part you're talking about right now.
Oh, this part right here?
Yeah.
Then you're ahead of the game. Then you can just listen to me talk. Okay, so the next part is saying simplify square roots. So when simplifying these square roots, if we know what the square root is, it's simply just, okay, we either recall it or we plug it into the calculator. So for example, the square root of 36 is 6. And we know that because 6 times 6 is 36. Or another way to think about this is 6 squared equals 36. Okay, another cool thing about the square root is that if you have the square root of a fraction, we can actually rewrite this based off the properties of square roots and give the square root to the numerator and the denominator separately. So this is actually the square root of 4 divided by the square root of 9, which looks a lot easier to solve than the square root of the entire fraction. So what would this simplify to? 2 over 3. Okay. For the ones that are decimals, okay, You can either look at the decimal, and since we have a very simple decimal like 0.04, we know that the 4 within the square root is a perfect square. So if we take the square root of 4, we get 2. The only thing with this is you could have trouble remembering where the decimal would go. So for these type of problems, I highly suggest you just plug it into the calculator. Okay. So when we take the square root, what happens is we end up moving one decimal to the right. So we took the square root of that 4, we know it's 2, but instead of writing 0.02, we move the decimal 1 to the right, and it's 0.2. Okay, that's a lot to remember, and you have the calculator, so might as well use it, especially for those decimals. Okay, what would the square root of negative 144 be? No solution. Why? Because the negative is where?
On the inside.
On the inside. That's completely different than the next one. Where's the negative on the next one? Outside. So what would the answer to this one be? Negative 12. Because we take the square root of 144, which is 12, and then we just bring the negative with it. Okay? We also knew that this was going to be negative 12 because 144 is the same as 12 times 12, or 12 squared. Okay. What would be the answer to the next one? No solution. And then what would be the answer to the last one? Negative 1/3, because the negative's on the outside, and then we can give the square root to both the numerator and the denominator. So the square root of 1 is 1, and what's the square root of 9? 3. So this is negative 1/3. Okay, so you could either remember how to do these, or for these type of questions, you could technically type every single one into the calculator and you'd get an answer. Even the square root of negative 144, if you type that into the calculator, you'll get an error message. So that tells you no solution. Okay, so now we're going to talk about the definition of an nth root. So it says b is an nth root of a if b to the n power equals a. So if we replace like n with 2, this is saying b is a square root of a if b squared equals a. So we're replacing whatever number or whatever root we're going to find with n. So it gives an example. So it says 2 is the square root of 4 because 2 squared is 4. Okay. 2 is the third root of 8 because 2 cubed is 8. So what we're doing here is we're taking our exponents and we're working backwards. Then it says 2 is the fourth root of 16 because 2 to the fourth power is 16. Remember, these are the same as saying 2 times 2. This is the same as saying 2 times 2 times 2. And then this one's the same as saying 2 times 2 times 2 times 2. Okay, that's what those exponents are telling us to do. They're telling us to take that number and multiply it by itself that many times. Okay. So then it says evaluating the nth root of a. Okay. So it says if n is greater than 1, then we have an even integer, and a is greater than 0, then the nth root of a is the positive nth root of a. All this is saying is that if this is greater than 1, meaning this number on the outside is greater than 1, and it's even, so 2, 4, 6, 8, etc., when we take that nth root, we are going to get a positive number. Okay. Versus if n is greater than 1, but it's odd. Okay, so now we're looking at Still the number on the outside, but notice instead of a 4, it's a 3. So now we have an odd number, okay? If we have an nth root of an odd number, then we are able to take the nth root of something that's negative. Okay, so notice here, we have the cube root of negative 8. Okay, because it's a odd integer, so it's 3, we're able to include a negative inside. Unlike this one up here, if this was the 4th root of negative 625, this would be no solution since this is even. So even, we can't have a negative. Odd, we can. And then lastly, it says the nth root of 0. No matter what that root is, we're going to get 0. The 5th root of 0 is 0. The 10th root of 0 is 0, etc. Okay, so the next part in this notes, I give you a table, and this table includes common perfect squares, perfect 4th powers, and perfect 5th powers. So you'll have these on the tests. So if worst comes to worst, you go back to this table and you find the number on there that it's asking you to do, and it will include the answer. Okay. However, you're going to notice that not every single one is on here, and that's why you have your calculator. Okay. So all of these can be turned into nth roots. For example, and I'm only going to go through a couple of them, this one here would be the same as writing the 4th root of 81 equals 3. So one is using an exponent, and one is using an nth root. This is going to be easy test for you then.
Yeah.
Yeah.
I can understand this. The other stuff I have issue with.
So then this one here, how would we rewrite that bottom one?
It would equal, so the 4th square root of 625 equals 5.
Good, the 4th root. So when we say square root, we're thinking of something to the power of 2. So when you have another value in, we no longer say the square part. So it's just 4th root, 5th root, 6th root, so on and so forth. That word root is that radical. Okay, so yes, the 4th root of 625 equals 5. Okay, what about this one over here? How would you write that? If we're turning it to radicals. The 3rd root
of 8 is 2.
Yes. The 3rd root of 8 equals 2. Okay, and you can do that for every single one. Okay, and you can also work backwards. If you're given a root, we could rewrite this in terms of exponents. Okay, so let's look at some examples. Starting off easy, right? What's the square root of 4? 2. And again, we know that this is 2 because 2 squared equals 4. Right? If we were using that table to help us, of course on the table I didn't give you perfect squares, I just gave you the cubes, 4ths, and 5ths, but that is what it would look like on the table. Okay. What about the cube root of 64? This is actually on the table. We could look at the table and find our answer. It's 4, right? So we'd say this is 4 because this is the same as saying 4 cubed equals 64. And here it is on the table. Okay, so we could go from exponent to radical, radical to exponent. Okay. Or you should be able to, I'm actually not quite sure. On the basic calculators, can you do an nth root?
You can just do the root.
The square root?
Yeah.
Could I see your calculator real quick? Yeah, let me see.
On a Texas Instrument, maybe.
That was just the basic one.
Like the basic. This is the only one that technically you should be using, right? The basic.
Yeah.
Yeah, that's what I'm
No, it doesn't. So since that calculator doesn't, I wouldn't use other calculators that do, because you're only going to have those type of calculators on the test. Okay, so then the next one says we have the fifth root of negative 32. So you should see here we have a negative, and then you're supposed to check this root here and see if the root is what? Odd. Is 5 odd?
Yes.
Yes, which means we can have the negative. Okay? So we could see if this is on our chart. The fifth root of 32, so we're looking for the number 32 to the fifth power on there. And that's right here. Okay? So that means that the fifth root of negative 32 is going to equal negative 2, right? Because we had a negative there that they did not. So negative 2. Okay. And again, because this is the same as saying negative 2 to the fifth power equals negative 32. Okay. We could do this a different way. Okay, let's say you don't want to rely on that table. Do you guys remember in the beginning when we did the prime factor tree?
Yes.
Okay, so when we divided the number all by prime numbers. So we could do that here. So ignore the negative for now. Let's go ahead and do the prime factor tree starting with 2. So how many times can 2 go into 32? 16. How many times can 2 go into 16?
8.
How many times can 2 go into 8? 4. How many times can 2 go into 4? 2. And we stopped because we ended with a
2. It's a prime number.
prime. And then this 5 out here, remember before we were circling pairs of 2's? Well, that's because it was the square root. Square 2. So now we're going to circle pairs of 5 because that's the number on the outside. Well, look, there's 5 right here. Which means once we circle our pair, right, we take one of those numbers out. So we take out the 2. And since it was negative, we're just going to bring the negative over here. So 2 different ways to look at it. Bless you. You could use the, bless you. We could use the prime factor tree. We could use our calculator. Well, no, we can't use our calculator. Prime factor tree and the table provided. Okay. So let's look at the next one. The fourth root of 81.
3.
Okay, and you found that using the table right here. Okay, we even wrote it out. The fourth root of 81 equals 3. So again, we're saying, okay, this equals 3 because that's the same as saying 3 to the fourth power is 81. And I know you should be able to check this part on the calculator, I believe. Can you do an exponent other than 2?
I don't think you can't even do that.
Oh, okay. Well, that's okay, right? Because that's the same as saying 3 times 3 times 3 times 3. I mean, it's going to take longer, but it's the same concept to check. Okay. What about this one?
10.
And how'd you get 10?
10 times 10 times 10 times 10 times 10.
Perfect. 6 times, right?
Yeah.
Okay, so for this one, this would be not impossible to do the prime factor tree, but it would take a very long time if we started with 2 and then kept going until we ended. Well, since this is just a large, what is this? A million?
Yeah.
Okay, so then we do what you said. We break it down and say, well, this is the same as saying 10 times 10 times 10, 6 times. And I know it's 6 times because how many zeros are there? 6. Okay, so since this is 10 times 10 times 10, 6 times, I can technically circle my pair of 6. Now I only have one pair of 6. That means my answer is 10. Or in other words, this is the same as saying 10 to the 6th power equals 1 million. Okay. What about this one?
We cannot.
Can't, right? So we say
No solution.
no solution. And why are we saying no solution?
Because it's even and there's a negative.
Even means we can't have a negative. No negative. So it's no solution. Okay, even though instinctively you should think, oh, well, we kind of did that problem already. I think it should be 2. But because of that even nth root, we cannot solve this yet. Don't worry, you'll learn how to solve in college algebra. When you learn about imaginary numbers.
Okay, so that's the only one I got wrong. I solved and got -2.
Yeah, and that's only going to be because this is even. We can't solve. The nth root, 4 is even. Okay, now let's look at the next concept that says roots of variable expressions. So it says if n is a positive odd integer, then the nth root of a to the n power is a. What that means is if we have our exponent matching our nth root, they cancel. And that's why we're just left with a. So that is only true if n is positive and odd. Okay. If n is positive and even, they still cancel out, but we have to equal it to the absolute value of a. Because if it's an even integer, remember, can we have a negative inside of the square root? Like, for example, if we had the 4th root, could we have a negative inside? No, so that's why we have to make sure our answer is the absolute value of a, because absolute value guarantees there's no negatives. Okay. So in this first example, we're first going to look at this and we're going to say, is it even or odd? Even. So that means I'm going to cross these out and make sure I write my answer inside absolute value. Good. So what's the absolute value of -3? 3. That's my answer. These are probably a nice mental break from last notes.
Yes.
Don't worry, it gets harder. Not in these ones.
Thank you.
Okay, so this one. Okay, it's even. Good. That's the first thing. It's even. Okay. So yes, it's going to be the absolute value. I think I did, this is a mistake. This should be 6. Because we're not there yet to where they're different numbers. Okay, so since they're both the same, we do what?
Cancel them out.
Cancel them out. Okay, and since this is even, we make sure to put our answer inside absolute value. So it's the absolute value of a plus b. And that's our answer.
It doesn't just become a plus b.
Wait, how did you get the 6 there?
It was a typo.
That would not work.
Say that again.
Would it not, it has to be with the matching,
In order to cancel them out, yes. Yes.
Are we gonna have to worry about the n and then the number in front of it being different at any point?
Yes.
Okay.
Yes, and I think we see that in this note, just not yet. So we can't just leave it as a plus b without the absolute value bars. Because of this, it said if we have an even integer, we have to include absolute value. which means if we were to plug in an A and B value that when we add it gave us a negative number, that absolute value bar would make sure it doesn't turn negative. It will always be positive. Okay, now this one is one I wanted to show you where they have difference. Okay, because if we don't see a number here, what can we assume the number is?
1.
Oh, this is a little different though.
0.
No. Remember I told you this is called a square root? So what number is square root? 2. Okay, and is this even or odd? Even. Okay, but notice now, are they the same? No, so we have to think, okay, y to the 4th is the same as saying y times y times y times y, correct? And that nth root tells us how many groups we can take out at a time. So that means I'm going to circle 2 pairs of 2. Which means when I take this out, this is going to be the absolute value of y times y, because I'm taking 1 y from this group and 1 y from this group. And I can simplify y times y to be y squared. So the answer is the absolute value of y squared. Another way you could think about it is you see the exponent on the inside. Well, what's 4 divided by 2? 2. Okay, 2 ways to think about it. However, that last way is only going to work if they give you whole numbers as your answer. Right? Like we couldn't say, okay, if this was a 5, that's a bad 5. If this was a 5, I couldn't do 5 divided by 2. That wouldn't give me a whole number. Okay, so that only works if it will give you a whole number as your answer. This way, drawing out your variables and circling the pairs will always work. Okay, any questions so far?
On the first question of the concept 3, why
Yes.
was the answer 3 and not negative?
Because that's the definition of absolute value, these bars. They always chop off the negative every single time, which means if we had the absolute value of 3, that's just 3, because there's no negative to take off.
This thing has to be touching for it to not lock, correct?
Correct. Correct. Okay. So now we're going to look at more examples where your nth root does not match your exponent. Okay. And then notice here I give you another nice little box of what it means to be a perfect square or a perfect cube. So we kind of talked about perfect squares already when we learned how to factor perfect squares. So you guys know that the perfect square, x squared, is the same as x times x. Okay? The perfect square, y to the 6, is the same as saying x cubed times x cubed. Okay? Because when you take the exponents, by property of exponents, they multiply. Okay? So x cubed squared is x to the 6. Okay? X cubed cubed is x to the 9th. So this part is talking about perfect cubes, which means you have to be able to, if we're thinking numbers, take the cube root of that number and get the same number to multiply. And so you can think of that even up here. Right here with these perfect cubes, well, the cube root of 27 is 3, because that's 3 times 3 times 3. They all match. Which means that the cube root of x to the 6th power is the same as saying x squared times x squared times x squared, which is x to the 6. Okay. So we're going to look at this one here. So if we don't see the nth root, we know that number is 2. Okay. This is also even. So that means in our answer, we're going to make sure to include the absolute value bars. And then we can check this way, like the second way we did. What's 8 divided by 2? 4. So this is equal to the absolute value of y to the fourth. Okay. Or what could you do? Y times y times y times y times y times y times y, right? 8 times. And then you would go through and circle pairs of 2. And how many pairs of 2 are there? 4.
Why would you circle in pairs?
Because of the square root, that nth root.
But why does that make it circle? So you circle in pairs.
Because when we take this...
Oh, so there's 2, so you circle through. Okay.
Yes, yes. If that number was 3, you would circle 3, so on and so forth.
And then when we did the 5, you just circled all the 5. No.
Yes, I just circled all the 5. Yep. Okay. Okay, so now we have numbers mixed with variables. So, no, we're just going to treat it as 2 separate things. We're going to do the cube root of 27 and then the cube root of a cubed. So, we know that 27 is the same as saying 3 times... Okay. Let me rephrase. I'll do the factor tree. 3 goes into 27 9 times. 3 goes into 9 3 times. This is a cube root, so I'm going to circle pairs of 3. Okay? And I only have one group of 3. So that means when I write this, this is going to equal 3. Then I go to the a's. Well, this is a cubed with a cube root. So what happens to those? They cancel, and then I'm just left with a. So my answer is 3a. So it's not harder. You just have to do 2 things, right, instead of just the 1. Okay.
How do you differentiate between the squares and the cubes? I'm not confused.
Wait, sorry, say that one more time.
How do you differentiate between the squares and the cubes?
This one here, when this number on the outside, if it doesn't show a number, it's the square root. That's how I know it was 2. If it gives us a number, then whatever number that is, it's either the 3rd root, which is the cube root, and then the rest of them don't have fancy names. It's just 4th root, 5th root, 6th root, etc. Okay, so for this one, remember our properties of roots say I can give it to the numerator and the denominator. So this is the 5th root of a to the 5th over the 5th root of b to the 5th. And what do you notice about the root and the exponent? They're the same, so what happens? They cancel on both. So that means I'm just left with what? A over b. And why am I not putting it in absolute value? Not because it's variables, because odd. This is odd. If it was even, I would have to put it in what?
In the
Absolute values. Okay.
So even absolute value and then odd is just
By itself, yep. Okay. I would say this is one of the harder ways that you would see it, right? Because not only do we have a fraction, we have numbers, we have an x variable and a y variable. But that's okay. We just treat it one step at a time. So first what I'm going to do is I'm going to bring my negative because it's on the outside. And I'm going to do the 4th root of 81 x to the 4th y to the 8th over the 4th root of 16. Because it's a fraction, I can give my radical to both the numerator and the denominator. Okay? Then off of the 81, I'm going to do the prime factor tree. Okay, I'll just do it off to the side, 81. Can 2 go into 81? No. Can 3? I think so. I just don't know what it is if someone wants to calculate that. 27. And then we know 3 goes into 27 how many times? 9. And 3 goes into 9 3 times. So we have 4 3s. And what's our nth root? 4. So I'm going to end up circling 4 3s. So all of them, right? Which means how many are coming out? No. 1, right? Because I only circled one group, so one of them are coming out. So far, I have -4 in my answer. That negative is just from the outside I'm going to carry with us. And the 4 is from the 4th root of 81. Then I look at these, okay, and I see this 4 and this 4, which tells me what?
Cancel out.
They cancel, so what's left over? Just x. So I bring that down to my answer. Okay. Then I look at this, and what can I do?
Multiply.
Is it minus, 8 minus 4?
Divide, right? 8 divided by 4 is 2. So what am I going to have on the outside? Y squared. And then on the bottom, I just have to find, well, what's the 4th root of 16? I don't think it's 4. 2. Because remember, I could do it off to the side. 16 is 2 times 8, 2 times 4, and 2 times 2. And how many 2's are there? 4. So I would circle how many groups of 4? 1 group of 4. So that means the 2 comes out from my group. So this is my answer. Oh, wait, this is not my answer. What did I forget? I brought the negative, the absolute value, this right here, which means what happens to the negative?
It goes away.
It goes away, okay? Because remember, the 4th root of a number means that has to be that same number multiplied 4 times. And if you do 4 times 4, that's 16. Times 4 is a number, and times 4 is a bigger number. Yes, if it was the square root of 16, then yes, it would be 4.
For 16, how do you know to do just one?
Because when I did the prime factor tree, and I got all the way down to my prime number, I had 4 2's, and I know to circle 4 based off this 4th root. So if it was 5, I would circle 5, 3, I would circle 3, etc. Okay, so this is just 4xy squared over 2. Because of that absolute value, it gets rid of the negative. Yeah, I'm not very good at mental math, right? Multiplying in my head. It gets my students all the time, my high school students, because they'll be like, you're the math teacher. Why don't you know this? And I'm always like, I can't calculate numbers in my head. I'm not a calculator. I know how to use a calculator, and that's all that matters. Okay, so I'm going to try to finish these last oh my gosh, we have more. No, it's my iPad's about to die, and I can't plug it in and plug it in at the same time. How about